Empty space is not empty at all. It is a vibrant, seething arena where particles wink in and out of existence, a concept known as the quantum fabric. This video will reveal how this cosmic nothingness is the source of everything, from the atoms in your body to the most distant galaxies. You will discover the hidden mechanisms that allow the universe to build itself from the void, fundamentally changing how you see reality. We will uncover why the vacuum of space holds infinite energy and how fleeting quantum fluctuations gave birth to all cosmic structure. By the end, you will understand the profound connection between emptiness and existence itself. What does it truly mean for something to come from nothing? Centuries before we probed the quantum realm, the greatest minds of antiquity were locked in a silent battle over nothing. In ancient Greece, the philosopher Democritus proposed a radical idea. He suggested that everything in the world was composed of tiny, indivisible particles called atoms, swirling and colliding in an infinite, featureless void. For him, this emptiness was necessary, a stage upon which the drama of matter could unfold. Yet his rival, Aristotle, vehemently disagreed. He argued that a true void was a logical impossibility. Nature, he believed, abhorred a vacuum. For Aristotle, what appeared to be empty space was instead a plenum, a field of potentiality brimming with unseen properties and awaiting form. This fundamental disagreement shaped Western thought for 2,000 years. One side saw a canvas of pure nothing, while the other perceived a hidden fullness. This was not merely academic. It was the first great attempt to answer a question that haunts us still. How can structure and substance arise from apparent absence? These classical debates established the very language we would later need to describe the quantum vacuum. They framed the conflict between void and plenum, between absolute emptiness and latent existence. Our modern understanding did not emerge from a vacuum itself, but was built upon this ancient foundation, a slow turning of the intellectual wheel that would eventually lead to a shocking revelation. The answer was waiting in the strange, probabilistic world of the 20th century. The quiet confidence of classical physics was about to be irrevocably broken. By the early 20th century, scientists peered deeper into the atom than ever before, and the solid, predictable universe they expected simply vanished. In its place, they found a realm of profound weirdness governed by probability and chance. This was the quantum revolution, and its first casualty was the very idea of emptiness. The German physicist Werner Heisenberg introduced a principle that would become a cornerstone of this new reality. The uncertainty principle states that on the tiniest scales, certain pairs of properties, like a particle's position and its momentum, are fundamentally linked. You cannot know both with perfect precision at the same time. The more you pin down one, the more the other becomes a blur of possibility. This isn't a limitation of our machines. It is a fundamental feature of reality itself. This inherent fuzziness has a stunning consequence for empty space. If you were to claim a region of space had exactly zero energy, you would be stating its energy with perfect certainty. But the uncertainty principle forbids such perfect knowledge. Therefore, even in what we call a vacuum, the energy can never be precisely zero. It must fluctuate. It jitters, it seethes with potential. This is the quantum vacuum, a dramatic departure from the static nothingness of old. Think of it like the surface of a calm sea on a windless day. From a distance, it appears perfectly flat and still. But if you could shrink down to the molecular level, you would see a chaotic dance. water molecules are constantly vibrating, colliding, and exchanging energy. The sea is never truly still, and neither is space. These quantum fluctuations are the modern expression of Aristotle's plenum, a hidden fullness bursting with activity. From this energetic jitter, particles and their antimatter counterparts can spontaneously blink into existence. They borrow energy from the vacuum itself, existing for a fleeting moment before they meet and annihilate each other, returning the energy loan. This endless, frantic dance of creation and destruction happens everywhere, all the time, in every cubic centimeter of the universe. The void is not empty. It is a fertile ground, a cosmic loom weaving the fabric of reality from threads of probability. How could such fleeting ghost particles possibly build the enduring world we see around us? The answer lies in the very first moments of everything. This frantic dance of creation and annihilation is made possible by a temporary loan from the cosmos itself. Heisenberg's uncertainty principle does more than just forbid perfect knowledge. It permits the universe to borrow energy. For vanishingly brief instants, the strict cosmic ledger that says energy must be conserved can be balanced later. This temporary overdraft allows pairs of virtual particles, one matter and one antimatter, to spark into existence from the void. They are called virtual not because they are not real, but because their lives are impossibly short. They are born, they interact, and they vanish back into the quantum static before any direct observation can catch them, repaying the energy debt almost immediately. Yet to call them mere mathematical ghosts would be a profound mistake, for they leave their fingerprints everywhere. You can actually witness their push and pull in a lab. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum. This is the setup for the Casimir effect. In the gap between the plates, only certain wavelengths of virtual particles can flicker into being. The space is too narrow to accommodate the full, wild spectrum of fluctuations that are popping off outside the plates. Outside, the quantum foam is a riot of activity pushing inward. Inside the gap, it is a relative quiet. This imbalance of pressure, more virtual particles pushing on the outer surfaces than from within the gap, forces the plates together. It is a measurable, physical force caused by the presence of nothing but seething, empty space. So this quantum vacuum is far from tranquil. It is a bubbling cauldron, a continuous fire of creation and destruction happening in every single point you can imagine. Every cubic centimeter of the room around you is teeming with these transient entities, a cosmic frenzy hidden behind a veil of perfect stillness. This endless activity is not just a curious side effect, it is a fundamental property of reality. It is the mechanism that transforms a featureless void into a universe pregnant with potential, hinting at how the grandest of all beginnings could have been sparked by the smallest of whispers. So where do these ghostly virtual particles even come from? The answer lies in a deeper layer of reality, one where the very idea of a solid particle dissolves into something far more fundamental. Welcome to the world of quantum field theory. This framework proposes that the universe is not, at its heart, a collection of tiny billiard balls. Instead, what we perceive as particles are merely tiny excitations, like vibrations or ripples, in invisible, all-pervasive fields that fill the cosmos. Think of the entire universe as a vast, still pond. This pond is not water but a field. Now drop a single pebble. The ripples that spread out are not the pond itself but disturbances within it. An electron is not a tiny speck, it is a localized ripple in the universal electron field. A photon of light is a ripple in the electromagnetic field. Every type of fundamental particle has its own corresponding field, a cosmic medium stretching throughout all of space and time. This changes everything about the nature of emptiness. Even when a field appears calm and still, when it is in its lowest possible energy state, it is not truly at rest. The uncertainty principle ensures that these fields are always quivering, always fluctuating. The virtual particles that wink in and out of existence are the direct result of these restless fields jittering at the quantum scale. The void is not a blank slate, it is a symphony of these foundational fields, each one humming with latent energy, waiting to be plucked. Perhaps the most famous of these is the Higgs field. This is not a field of force but one of resistance. As certain particles move through the cosmos, they interact with this omnipresent Higgs field. This interaction is what grants them the property we experience as mass. A particle that moves freely, like a photon, does not interact with the Higgs field and remains massless. One that gets bogged down and resisted gains mass. The Higgs field is the cosmic molasses that gives substance to the universe, transforming ethereal energy into tangible matter. So space is no longer a passive stage where particles perform. Through the lens of quantum field theory, empty space is revealed as the active, dynamic participant. It is the actor, the director, and the stage all at once. These fundamental fields are the true quantum fabric, the warp and weft of existence itself. Their constant, low-level hum is the reason true nothingness is an impossibility. This vibrant, energetic vacuum was the perfect breeding ground for the most spectacular event of all, a period of unimaginable growth that set the stage for everything to come. This ghostly push from the void is not just theoretical. It was captured in a lab, proving that empty space itself can exert a physical force. The key to this discovery was a Dutch physicist named Hendrik Casimir. In the late 1940s, he and his colleague Dirk Polder devised a brilliantly simple experiment. They imagined taking two perfectly flat, uncharged metal plates and placing them parallel to each other, separated by a microscopic gap in a perfect vacuum. According to the classical physics of the time, nothing should happen. With no gravity, no electromagnetism, and no air pressure, the plates should remain perfectly, utterly still. But Casimir predicted a different outcome, one born from the quantum fizz of the vacuum. He realized that the space between the plates is too narrow for all the possible wavelengths of virtual particles to flicker into existence. Only certain waves, those whose wavelengths fit neatly between the plates like notes on a vibrating string, can form there. Outside the plates, however, the quantum vacuum is a riot. Virtual particles of every conceivable wavelength pop into being, creating a cacophony of pressure. The result is an imbalance. The chaotic dance outside pushes on the plates more strongly than the limited set of waves pushing from within the gap. This difference in pressure creates a net force that draws the plates together. It is a minuscule effect, measurable only when the plates are incredibly close, but it is undeniably real. When scientists finally performed this experiment with the required precision, they saw the plates move. They witnessed with their own instruments the tangible push of nothingness. The Casimir effect stands as one of the most direct and elegant validations of quantum field theory. It transforms the quantum vacuum from a mathematical abstraction into a physical entity that we can measure and test. It shows us that what we perceive as emptiness is in fact a dynamic medium. It's hidden energy capable of moving objects and shaping reality on the smallest scales. This confirmation raises a profound question. If the vacuum holds so much latent power, could it have been the engine for the most dramatic event in cosmic history? This restless energy of the vacuum has a name and a staggering implication. We call it zero-point energy, the absolute minimum vibrational energy that remains even when a quantum system is cooled to the coldest possible temperature, absolute zero. At this theoretical point, all classical motion would cease, but in the quantum world, the show never stops. The uncertainty principle forbids complete stillness. A particle can never truly be at rest, because that would mean we know its position and momentum with perfect, absolute certainty. So it must always jiggle, always hum with a residual, fundamental energy that can never be siphoned away. The scale of this energy is almost incomprehensible. Calculations suggest that within the volume of a single light bulb, the zero-point energy of the vacuum could be vast enough to boil every ocean on our planet. This is a truly infinite reservoir of power, woven into the fabric of space itself. So why don't we see this energy exploding all around us? The answer lies in its very nature. This energy is a baseline, the default state of reality. We only notice its effects when we change the conditions, like in the Casimir effect, where we alter the available space and the energy difference becomes a measurable force. Most of the time, this infinite energy is perfectly balanced and uniform, a constant background hum that cancels itself out from our perspective, yet its influence is undeniable. It is the zero-point jitter that drives spontaneous emission, the process where an atom in an excited state suddenly, unpredictably, decides to release a photon of light and drop to a lower energy level. There is no external trigger. It is the atom responding to the gentle, constant nudges of the quantum vacuum. This boundless, untappable energy reservoir forces us to reconsider the very nature of nothing. The vacuum is not merely a stage for particles, it is an active, energetic medium. Its ceaseless fluctuations, fueled by zero-point energy, sustain the quantum fabric, allowing virtual particles to dance and fields to vibrate. This hum was present at the very dawn of time, a primordial ocean of potential. Could this infinite energy of the void have been the catalyst that set our entire cosmic story in motion? But this ceaseless quantum jitter hints at an even deeper, more fundamental turbulence. If we could peer into the fabric of space-time at an unimaginably small scale, a realm known as the Planck length, the smooth, geometric universe described by Einstein would dissolve into chaos. Here, space-time itself is no longer a serene and continuous stage. Instead, it becomes a seething, frothing ocean, a turbulent foam of unimaginable density. This is the quantum foam, a concept pioneered by the physicist John Wheeler. In this realm, the very concepts of before and after lose their meaning. Tiny wormholes, bridges connecting different points in space, blink in and out of existence. Microscopic bubbles of distorted geometry form and pop in a frenetic dance. The smooth continuum of relativity shatters, revealing a granular, probabilistic underpinning to reality itself. This foam is the ultimate texture of the quantum fabric, the raw, unrefined state of existence. To visualize this, think of the surface of a carbonated drink. From a distance, it looks like a smooth, clear liquid, but up close, you see a chaotic effervescence with countless bubbles constantly forming, merging, and bursting. The quantum foam is like that, but for the stage of reality itself. It is space and time in a state of constant, violent reinvention. How could such a fundamental turbulence remain hidden? The scale is the key. The Planck length is so inconceivably tiny that a single atom is, by comparison, as vast as a galaxy. This is why our everyday world feels solid and continuous. We are simply too large, our perception too coarse, to feel the individual bubbles in the cosmic foam, yet their collective effect might be felt across the universe. This foamy structure could subtly alter the path of light traveling across billions of light years, or influence the way gravity behaves on the smallest scales. It represents the ultimate marriage of geometry and quantum weirdness, where the shape of reality is dictated by probability and fluctuation. The universe is not built on a firm foundation, but on a dynamic, ever-shifting quantum texture, a reminder that nothing, not even the void of space, is ever truly at rest. This strange, foamy foundation of reality has a startling consequence, a loophole in the laws of physics that allows the impossible to happen. Quantum tunneling is the phenomenon where a particle can suddenly appear on the other side of an energy barrier, like a ghost walking through a solid wall. In our everyday world, if you roll a ball up a hill, it will only reach the top if you give it enough energy. If it does not have that energy, it will roll back down. The hill is an impassable barrier, but in the quantum realm, particles do not behave like tiny balls. They behave like smeared-out waves of probability. This wave-like nature means a particle does not have a single, definite location. There is a small but real probability that the particle is already on the other side of the hill. It is not that the particle smashes through the barrier. Instead, its probability wave extends through it, and there is a chance the particle will simply manifest where, according to classical rules, it could never be. This is not a theory. It is a fundamental process that makes our universe work. Inside the heart of every star, including our own sun, hydrogen nuclei need to collide and fuse to create helium and release the energy that gives us light and warmth. But these nuclei are all positively charged, and they repel each other fiercely. The electrical repulsion between them is a massive energy mountain they should not be able to climb. They simply do not possess enough thermal energy from the star's heat to overcome it. Without quantum tunneling, stars would be dark. The sun would never have ignited. Yet, because of their quantum wave nature, there is a tiny probability that these hydrogen nuclei will tunnel through that immense repulsive barrier and fuse. This happens countless times every second, a cosmic miracle powered by a quantum cheat code. This same principle is the engine inside many of our modern electronics. The transistor, the fundamental switch in every computer chip, relies on electrons tunneling through barriers to create the ones and zeros of digital information. The device you are using right now to watch this depends on particles performing impossible feats billions of times per second. So tunneling demonstrates a profound truth about the quantum fabric. The voids and barriers we perceive are not absolute. They are permeable, threaded through with probability. What seems like an impassable nothingness, a wall of non-existence, is actually a gateway shimmering with potential. If particles can tunnel from one state of being to another, could the entire universe have done the same? But the very field that grants substance to our universe might also contain the seeds of its ultimate demise. The Higgs field, the cosmic molasses that gives particles mass, might not be in its most stable, lowest energy state. Instead, it could be resting in a precarious condition known as a false vacuum. Think of our universe as a ball sitting in a small dip on the side of a vast, sloping mountain. This dip is stable enough for now. It feels like a comfortable valley. But far below lies a much deeper valley, representing the true vacuum, the lowest possible energy state for the Higgs field. Our cosmic ball could, in theory, suddenly tunnel through the mountainside and roll down into that deeper valley. This is the terrifying concept of vacuum decay. It would begin with a single, random quantum event, a tiny bubble of true vacuum spontaneously forming somewhere in space. The moment this bubble appears, the laws of physics as we know them would be rewritten within its boundary. The properties of matter would instantly and fundamentally change. Atoms would no longer hold together. The very forces that govern reality would cease to function in any recognizable way. This bubble of new reality would then expand at the speed of light, a sphere of annihilation whose edge would offer no warning. One moment, the universe exists as we know it, the next, it is erased and replaced by something entirely alien. There would be no cataclysm to witness, no sound or flash. The transition would be instantaneous and complete, rewriting the cosmos from the ground up. What makes this more than a dark fantasy is the mathematics. Our current measurements of the Higgs boson and the top quark suggest that our vacuum is indeed metastable, balanced in that shallow dip on the mountainside. The unsettling truth is that the quantum fabric is not a static tapestry. It is a dynamic, shifting landscape, and the emptiness beneath it all holds the potential for radical transformation. This reveals a profound precariousness to existence, a universe born from fluctuation and potentially destined to end by one. Even the most absolute prisons in the universe are not immune to the restless activity of the quantum fabric. Stephen Hawking made a startling prediction that forever changed our understanding of black holes. He proposed that these gravitational monsters, from which not even light can escape, are not eternally dark. They can, in fact, glow, slowly leaking radiation until they potentially vanish. This phenomenon, now known as Hawking radiation, arises from a delicate interplay between gravity and the quantum vacuum at the very edge of a black hole, the event horizon. The process begins with the same virtual particle pairs that flicker in and out of existence everywhere in space. Normally, these pairs annihilate each other almost instantly. But at the event horizon, where gravity is so immense that space-time is sharply curved, a strange separation can occur. Imagine a virtual particle and its antimatter partner popping into being right at this cosmic point of no return. One particle might appear just outside the horizon, while its partner appears just inside. The one outside could escape, carrying energy away into the universe. Its trapped partner, unable to exist on its own, must fall inward, carrying negative energy with it. To balance the cosmic books, this negative energy reduces the black hole's total mass. The escaped particle becomes real, a genuine piece of radiation streaming away from the black hole. This is not a violent explosion. It is a slow, quiet leak of energy, one particle at a time. The black hole pays for this radiation with its own mass, slowly shrinking over astronomical eons. For a stellar mass black hole, this process is incredibly slow, taking far longer than the current age of the universe to become significant. But for a much smaller, theoretical black hole, this evaporation could eventually lead to its complete disappearance. Hawking's brilliant insight connected three great pillars of physics: gravity, quantum mechanics, and thermodynamics, showing they are deeply intertwined. This radiation reveals that even the most destructive forces in the cosmos are part of a grand cycle. The energy locked away in a black hole's grip is not lost forever. Through the subtle magic of quantum fluctuations, it can be slowly returned to the universe, perhaps to one day form new stars, new planets, or new possibilities. This cosmic recycling, powered by the vacuum itself, shows that existence is a continuous dance of transformation, where endings are merely preludes to new beginnings. This cosmic molasses we call the Higgs field does more than just fill the void. It actively sculpts the character of our universe by answering a fundamental question. Why do different particles have different masses? The answer lies not in the particles themselves, but in how they interact with this invisible, all-pervasive field. When the universe was young and unimaginably hot, the Higgs field was in a symmetrical state, its value hovering around zero. In this primordial heat, all fundamental particles were massless, zipping through the cosmos at the speed of light. They were pure, unhindered energy, but as the universe expanded and cooled, a profound shift occurred, much like water vapor condensing into liquid. The Higgs field settled into a new, stable state, a non-zero value that now fills every corner of space. This transition is what we call the Higgs mechanism. It broke the symmetry of the early universe and gave particles their mass. Think of it like moving through a crowded room. A famous person trying to get to the other side would be swarmed by admirers, their progress severely slowed by the constant interactions. They experience a great deal of drag, and this is analogous to a particle with high mass. An unknown individual, however, could glide through the same room with ease, interacting with almost no one. They experience very little drag, much like a low-mass particle. The photon, the particle of light, does not interact with the Higgs field at all. It moves through the cosmic crowd completely unnoticed, which is why it remains massless and travels at the ultimate speed limit. An electron interacts just a little, giving it a small amount of mass. The quarks that make up protons and neutrons interact quite strongly, resulting in significantly more mass. This simple yet profound idea redefines what mass is. It is not an intrinsic property carried by a particle. It is a measure of a particle's interaction with the cosmic Higgs field. The discovery that confirmed this breathtaking picture was the Higgs boson itself. This particle is not the field, but a crucial piece of evidence for its existence. In quantum field theory, a fundamental field can be excited, and that excitation manifests as a particle. A ripple in the electron field is an electron. A ripple in the Higgs field is the Higgs boson. Finding this ripple was the goal of the Large Hadron Collider, the most powerful particle accelerator ever built. By smashing protons together at velocities incredibly close to the speed of light, scientists recreated the intense energies of the early universe. In the aftermath of these collisions, for a fleeting fraction of a second, the Higgs field was jostled, and from that disturbance, the Higgs boson flickered into existence before decaying into other, more stable particles. Its telltale signature was detected in 2012, a triumphant moment that confirmed a decades-old prediction. The Higgs mechanism shows us that the quantum vacuum is not a passive backdrop. It is an active participant that dictates the very rules of the game. The diversity of matter, the very fact that stars can form and planets can coalesce, hinges on this field's subtle influence. Without it, the universe would be a sea of massless energy, a formless, high-speed blur with no structure and no chance for life as we know it. The quiet hum of the Higgs field gave the cosmos its substance, its texture, and its stunning variety. This quantum jitter, this endless flickering in the void, would become the most important blueprint in cosmic history. To understand how, we must travel back to the first sliver of a second after the Big Bang, to a theory known as cosmic inflation. For a breathtakingly brief moment, the universe was not expanding, it was exploding. A peculiar quantum field, often called the inflaton field, locked space into a state of negative pressure. This triggered a phase of exponential expansion, causing the cosmos to double in size over and over again, faster than the speed of light. In less time than it takes to blink, a subatomic speck of reality was stretched to a size larger than our entire observable universe today. This wasn't just an expansion of space, it was the stretching of the quantum fabric itself, and as it stretched, it pulled on the fabric's intrinsic texture. Those tiny, random quantum fluctuations, the virtual particles dancing in and out of existence, were not left behind, they were magnified. Imagine taking a perfectly smooth sheet of silk and stretching it violently in all directions. Any microscopic imperfections in the weave, any tiny bumps or wrinkles, would be blown up to macroscopic proportions. Inflation did exactly this to the quantum foam. The microscopic ripples in the inflaton field became vast hills and valleys in the density of the newborn cosmos. These density variations are the primordial seeds for all structure. Where the density was slightly higher, gravity had a little more to work with, slowly pulling matter together over billions of years. Where it was slightly lower, matter became more sparse. From these quantum imprints, the great cosmic web of galaxies, clusters, and superclusters eventually crystallized. The randomness of the microcosmos was written large across the macrocosmos. We can still see the echo of this event today, frozen in time. The cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, is not perfectly uniform. When we map it with satellites, we see a mottled pattern of tiny temperature differences, a celestial fingerprint. Those spots, those minute variations, are the direct descendants of the quantum fluctuations stretched by inflation. They are a baby picture of the universe, showing the density seeds that would one day become everything we see. This is perhaps the most profound connection ever discovered. It ties the ghostly, probabilistic world of quantum mechanics directly to the grand, gravitational architecture of the cosmos. The same uncertainty that allows a particle to tunnel through a barrier also gave us the Milky Way. The same vacuum energy that pushes plates together in a lab also crafted the voids between galaxies. Inflation demonstrates that our universe is not just quantum at its heart, it is quantum in its very skeleton. The emptiness, it turns out, was always pregnant with form, waiting only for the right moment to unfold. This profound interconnectedness does not stop at the birth of galaxies. It reaches down to the very heart of how particles relate to one another, challenging our most basic assumptions about space and distance. Quantum entanglement is a phenomenon so strange that Albert Einstein himself famously dismissed it as spooky action at a distance. It describes a situation where two particles become linked in such a way that the state of one is instantly connected to the state of the other, no matter how far apart they are separated. You could take one particle to the farthest edge of the observable universe, and a measurement performed on its partner would influence it immediately. This connection appears to happen faster than light, defying classical logic. How can information seem to travel without any time delay? The answer forces us to reconsider what information and location even mean. In the entangled reality, these two particles are not two separate entities sending signals. They are part of a single, unified quantum system. Their connection is not transmitted through space. It is a fundamental property that exists outside of it. Space, with its vast distances, might not be the primary stage of reality. It could be a secondary effect, an emergent property that arises from a deeper, more fundamental layer of quantum relationships. The void is not just a seething foam, it is a woven tapestry with invisible threads connecting every part to the whole. This idea was put to the test in a series of brilliant experiments inspired by physicist John Stuart Bell. Bell tests provided a way to distinguish between a universe where particles have hidden, predetermined states, as Einstein hoped, and one where their properties are truly linked in this spooky way. The setup often involves creating pairs of entangled photons and sending them in opposite directions to detectors that can measure their properties, like polarization. If Einstein was correct, there would be a statistical limit to how often their measurements could agree, a limit based on local, hidden variables. Yet, time and again, the experiments have shown correlations that surpass this classical limit. The particles agree with each other more often than they should if they were independent. This result strongly suggests that there are no hidden variables, no secret instructions the particles carry with them. Their connection is real, non-local, and instantaneous. It is a feature of the quantum fabric itself. This has profound implications. It suggests that what we perceive as empty space, the vast void separating stars and galaxies, might be an illusion built from countless entangled relationships. The universe may be far more unified than it appears, a single, coherent system that only looks fragmented from our limited perspective. If particles can share a state across any distance, then the very idea of separateness begins to dissolve, hinting at an underlying oneness from which all of existence is born. This intricate web of quantum connections leads to a startling question about our own place in the cosmos. The fundamental constants of nature seem to be perfectly calibrated for life. The strength of gravity, the force binding atoms, the mass of an electron, each of these values is a dial on the cosmic control board. If any one of them were turned even slightly, the universe would be unrecognizable. A little stronger, and the universe would have collapsed back on itself moments after the Big Bang. A little weaker, and no galaxies or stars would ever have formed. The balance is so precise it seems to defy mere chance, as if the universe knew we were coming. This remarkable fine-tuning finds a potential explanation in a controversial idea known as the Anthropic principle. In its simplest form, it states that we observe the universe to have these specific properties because only in such a universe could observers like us exist to ask the question. We are not seeing a designed cosmos but a survivable one. This shifts the perspective from why the universe is fit for life to how we find ourselves within a universe that allows it. Perhaps these constants are not fixed laws, but are instead the local bylaws of our particular cosmic neighborhood, set by the specific way our quantum vacuum settled into its current state. The properties of that vacuum, the specific values of its fields, could have locked in the forces and masses we now measure. This opens the door to a breathtaking possibility, the multiverse. If the quantum foam can spawn particles and inflation can spawn entire universes, then perhaps our reality is just one bubble in an infinite, frothing ocean of other universes. In this vast cosmic tapestry, each universe might have its own random set of physical constants, a product of unique quantum fluctuations during its birth. Most of these universes would be stillborn or barren, their numbers set to values that never allow for complexity, but in a rare few, by sheer statistical chance, the numbers line up just right. We, of course, find ourselves in one of those rare, hospitable pockets. The debate this inspires is profound. Does this intricate fine-tuning point toward a deeper purpose, or is it simply the result of a cosmic lottery with an almost infinite number of tickets? The quantum fabric offers a compelling, if humbling, answer. It suggests that our reality is not a unique creation, but one specific expression of the vacuum's infinite potential. The void does not favor life, it simply allows for every possibility, and we are the ones who emerged from a particular roll of the quantum dice. This ties our existence directly back to the seething energy of empty space. The same quantum fluctuations that seeded galaxies also set the stage for life itself, implying that we are not just living in the universe, but are a vibrant expression of its most fundamental, restless nature. This accelerating expansion points to a force hidden within the void itself. For decades, cosmologists assumed the gravitational pull of all the matter in the cosmos would eventually slow the universe's growth, perhaps even reverse it in a great crunch. Then, in the late 1990s, two independent teams of astronomers made a shattering discovery. By observing distant supernova, the explosive deaths of stars, they found that the universe is not slowing down at all. It is speeding up. The fabric of space itself is stretching faster and faster, as if pushed by an invisible hand. This discovery earned them the Nobel Prize and forced a complete rewrite of our cosmic story. The driver of this acceleration was given a simple yet profound name: dark energy. It is not a ghost or a spirit, but a property of space. Even in a perfect vacuum, devoid of all matter and radiation, this energy persists. It is the energy of the quantum fabric itself, and it possesses a strange characteristic: negative pressure. Think of a stretched rubber band. It has positive pressure pulling inward, trying to snap back. Now imagine a substance that does the opposite. When stretched, it pushes outward, resisting the pull and expanding even further. This is the bizarre nature of the dark energy permeating the cosmos. It is the anti-gravity woven into the fabric of nothingness. The leading explanation for this phenomenon is Einstein's cosmological constant, a term he originally inserted into his equations to keep the universe static, later calling it his greatest blunder. He was right to introduce the idea, but for the wrong reason. The cosmological constant represents the baseline energy density of empty space, a constant push inherent to the vacuum. This energy could directly stem from the ceaseless fluctuations of quantum fields, the same ones responsible for virtual particles. While the energy of individual fluctuations is minuscule, when you add up the contribution from every single point in the vast expanse of the universe, the total becomes immense, dominating the cosmic energy budget and dictating the fate of everything. The evidence for dark energy is now overwhelming. It is etched into the large-scale structure of the universe in the way galaxies cluster, and it is written in the faint afterglow of the Big Bang. Dark energy is not a small effect. It makes up about 68% of the entire mass-energy content of the cosmos. We are living in a universe ruled by the energy of emptiness. This turns our intuition on its head. The quantum fabric is not a passive stage for the celestial drama. It is the lead actor, actively shaping the evolution and ultimate destiny of the cosmos. The same void that gave birth to galaxies through inflation is now tearing them apart, pushing them into an ever-deepening isolation. This reveals a profound duality. The vacuum is both the creative source of all structure and the force that will ultimately dissolve it into an ever-cooling, ever-expanding stillness. These infinities were a profound embarrassment for the theory. When physicists first attempted to calculate simple properties, like the mass or charge of an electron, their equations would often spit out a result of infinity. This was a clear sign that something was deeply wrong, or at least deeply incomplete, in their description of reality. The problem stemmed from the quantum vacuum itself. To calculate the properties of a single electron, you had to account for its interactions with every possible virtual particle that could flicker into existence around it. This involved summing up an infinite number of increasingly unlikely but still possible quantum events. The result was a mathematical disaster, an infinite sum that made the theory seem useless for making real predictions. The universe, after all, is not infinite in its everyday behavior. Electrons have a very specific, finite mass and charge. So how do we reconcile the infinite possibilities of the quantum world with the finite facts we measure? The answer is a mathematical sleight of hand known as renormalization. Think of it this way. Imagine you are trying to weigh a single, specific fish in the ocean. The fish is constantly surrounded by water, and its scales are covered in a thin film of it. If you just scoop the fish out and put it on a scale, you would be measuring the fish plus all that clinging water. To find the true weight of the fish alone, you would need to subtract the weight of the water. Renormalization works on a similar principle. The infinite results from the math are not the true, bare properties of the particle. They are the particle plus the overwhelming background noise of the quantum vacuum. Physicists realized they could carefully separate these two things. They define the measured, finite values, the mass and charge we actually observe in experiments, as the real starting points. The infinities from the vacuum fluctuations are then systematically absorbed into these definitions, effectively canceling them out. It is a process of subtracting one infinity from another to yield a finite, sensible answer that perfectly matches what we see in the world. This is not cheating. It is a recognition that we can never observe a naked particle divorced from its quantum environment. What we measure is always the particle dressed in its interactions with the void. Renormalization is the process of tailoring that clothing to fit the data. Through this ingenious method, the messy, chaotic quantum vacuum is tamed. Its infinite energy is corralled and made to serve the equations, allowing us to make stunningly accurate predictions. The entire standard model of particle physics, which describes all known fundamental particles and forces, is a renormalizable theory. Its ability to cancel these infinities is what makes it so powerful and so precise. The process reveals a deep truth beneath the apparent chaos. The quantum fabric, for all its seething randomness, operates under a consistent, logical set of rules. We may need clever mathematical tools to see through the static, but the signal of reality is always there, clear and finite, waiting to be decoded. This successful taming of infinity begs a final, monumental question. If we can cancel the infinite energy of the vacuum to understand particles, could the entire cosmos be the result of a similar, primordial balancing act? But what does it truly mean to observe something? This question lies at the heart of one of the most perplexing mysteries in all of physics, the measurement problem. In the quantum realm, a particle like an electron does not have a definite location or state until the moment it is measured. Before that observation, it exists in a blur of all possible states at once, a condition known as a superposition. It is only when a measurement is taken, when a conscious observer or a measuring device interacts with it, that this cloud of potential collapses into a single, concrete reality. This sudden transition from possibility to fact forces us to confront a staggering idea. The act of looking, of gathering information, might be an active participant in the creation of the world we perceive. The implications ripple all the way down to the quantum vacuum itself. If the void is a sea of infinite potential, a frothing ocean of virtual particles in superposition, then what determines which possibilities become real? Does the presence of an observer, in some fundamental way, influence the outcomes that emerge from the emptiness? This is where the interpretations of quantum mechanics diverge into fascinating and sometimes unsettling paths. The Copenhagen interpretation, championed by figures like Niels Bohr, posits that the wave function, which describes the probability cloud of a particle, objectively collapses upon measurement. In this view, the observer is separate from the system and plays a crucial role in actualizing reality. The quantum world remains in a state of potentia until it interacts with the classical world of the observer. Another perspective, the many worlds interpretation, offers a different solution. It suggests that the wave function never collapses at all. Instead, at the moment of measurement, every possible outcome actually occurs, but each one plays out in a newly branched parallel universe. In one world, you measure the electron to be spinning up. In another, an identical version of you measures it to be spinning down. Both realities are equally real, splitting off from one another continuously. In this breathtaking picture, the quantum vacuum does not choose one outcome. It manifests all of them, weaving an infinite tapestry of parallel existences from its foundational fluctuations. So where does that leave the line between the emptiness of the void and the solidity of something? The observer effect blurs this distinction profoundly. It hints that awareness, or at the very least a physical interaction that conveys information, is not a passive witness to a pre-formed reality. It is intertwined with the very process of manifestation. The something we call the universe may not emerge from nothing without a relationship, a kind of cosmic conversation between the seething potential of the quantum fabric and the act of observation that gives it definition. This does not require human consciousness, but any interaction that leaves a lasting record, that distinguishes one possibility from another. The quantum vacuum, in its infinite creativity, offers every possible story. It is through the act of measurement, of interaction, that a single narrative is selected and experienced. This suggests a universe where existence is not a solitary state, but a relationship, a dance between the unmanifest and the manifest, between the silent question of the void and the resonant answer of a thing observed. The universe began in a state of perfect, almost featureless symmetry. Every force was unified and particles were indistinguishable, a realm of pure potential. But as the cosmos expanded and cooled, it underwent a series of profound transformations, like a single substance crystallizing into many different forms. This is the process of symmetry breaking, the hidden mechanism that carved diversity from a blank canvas of uniformity. Think of a perfectly round ball balanced on the tip of a very sharp hill. In that moment, the situation is perfectly symmetrical. There is no reason for the ball to fall in any particular direction, but the slightest disturbance, a breath of wind, will cause it to roll down one specific side. The perfect symmetry is broken and a specific direction is chosen, creating a new, stable, but less symmetrical reality. This is precisely what happened in the early universe as it transitioned from an unimaginably hot, dense state. One of the most critical breaks occurred with the electroweak force. In the first fleeting moments, the electromagnetic force and the weak nuclear force were not two separate things. They were one and the same, a single electroweak interaction. The particles that carry these forces, photons and W and Z bosons, were also identical massless entities. But as the temperature plummeted, the Higgs field, which had been hovering at a zero value, settled into a new, stable state everywhere at once. This event, known as the electroweak phase transition, broke the symmetry. The once unified force splintered. The photon remained massless, becoming the carrier of the electromagnetic force we know, the force of light and chemistry. The W and Z bosons, however, interacted strongly with the now active Higgs field, and they became incredibly massive. This acquisition of mass is what fundamentally changed their role, confining the weak nuclear force to an extremely short range, governing processes like nuclear fusion inside stars. Without this crucial breaking of symmetry, atoms as we know them could not exist. The distinct forces necessary for building complex structures simply would not be there. The universe would remain a soup of undifferentiated particles, unable to coalesce into the ingredients for stars, planets, or life. This transition from unity to diversity did not stop there. Similar symmetry breaks are thought to have occurred even earlier, potentially separating the strong nuclear force from the electroweak force, each step carving out a new set of rules for reality. The quantum fabric did not remain a smooth, featureless plane. It developed texture, hills, and valleys of potential energy as its various fields settled into their stable states. From a primordial emptiness of perfect symmetry, the act of breaking that symmetry generated the very particles and forces that would go on to build everything. It was the moment the cosmic loom began weaving its intricate patterns, transforming a silent potential into the rich, complex, and tangible universe we call home. This great challenge of modern physics pits two titans of understanding against one another. On one hand, we have Einstein's general relativity, a masterpiece that describes the cosmos on its grandest scales, where gravity is the elegant curvature of space-time itself. On the other, we have quantum mechanics, the wildly successful rulebook for the atomic and subatomic world, a realm of probability and fluctuation. Both are brilliantly accurate within their own domains, yet they speak completely different languages and become mutually incomprehensible when forced to meet. Their conflict becomes most apparent in the most extreme environments, like the center of a black hole or the very first moment of the Big Bang, where immense gravity acts on a quantum scale. To understand the origin of everything, we must find a theory that can unite them, a framework of quantum gravity. The leading candidates for this unified theory propose a radical reinvention of the quantum fabric itself. String theory suggests that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. An electron is not a dot, it is a string vibrating at one specific frequency. A quark is the same type of string vibrating at a different frequency, much like a single violin string can produce different notes. In this picture, gravity emerges naturally from the vibrations of a particular type of string, the graviton. But for the math to work, string theory requires something startling, extra dimensions of space beyond the three we experience, all curled up into sizes far smaller than an atom. Loop quantum gravity takes a different, equally mind-bending approach. It proposes that space itself is not a smooth, continuous backdrop. Instead, it is woven from a network of finite, discrete loops, a fabric of interconnected threads. Picture a tapestry. From a distance, it looks like a smooth, continuous sheet, but up close, you see it is made of individual, woven threads. In loop quantum gravity, space has a granular structure, a smallest possible unit of volume, preventing the infinities that plague other theories. Here, gravity is a direct consequence of this quantized geometry. Both theories, in their own way, attempt to describe how gravity itself might be born from the deeper chaos of the quantum vacuum. They seek to show that the force which shapes galaxies is not fundamental, but emergent, a large-scale consequence of the collective behavior of spacetime's most basic building blocks. The implications for the origin of the universe are profound. If space and time are quantized, then the Big Bang was not a singular point of infinite density, but a quantum transition, a great bounce from a previous cosmic phase. The pursuit of quantum gravity forces us to confront the ultimate nature of the void, suggesting that the true foundation of reality is a realm of pure relation, where the very concepts of here and there are woven from a deeper, more fundamental connectivity. This radical rethinking of space and information leads to one of the most astonishing ideas in modern physics. The holographic principle proposes that our experience of a three-dimensional universe is a magnificent illusion, a projection from a distant, two-dimensional surface. All the information needed to describe everything within a volume of space, every star, every person, every atom, could be encoded on its outer boundary like a cosmic DVD. This concept emerged from a profound puzzle about black holes. When an object falls into a black hole, it seems to vanish, taking its information with it. This violates a core quantum rule that information can never be truly destroyed. Physicists discovered that the maximum amount of information a region of space can contain is not proportional to its volume, but to the area of its surface. A black hole's entropy, a measure of its hidden information, is tied directly to the area of its event horizon. This suggests that the entire contents of the black hole are somehow painted onto its surface. The holographic principle takes this black hole thermodynamics and applies it to the entire cosmos. In this view, our three-dimensional reality is a holographic projection from a vast, shimmering shell of encoded data at the edge of the observable universe. We are not living inside the volume, we are living on a projection from its surface. This completely inverts our intuition about reality. Emptiness is not empty at all, it is saturated with information. The quantum vacuum is not a chaotic foam, but a computational surface, a screen onto which the universe is rendered. Think of a credit card hologram. The flat, shiny surface seems to contain a three-dimensional image that you can look around. The holographic principle suggests our universe operates on a similar, though far more fundamental, level. The smooth, continuous space we move through is a convenient and convincing illusion generated from a vast network of quantum bits residing on a distant two-dimensional surface. This has staggering implications for the nature of the quantum fabric. The frenetic dance of virtual particles, the seething energy of the vacuum, all of it could be the projected image of processes happening on that foundational screen. The forces we feel, the particles we see, are all manifestations of information being processed and displayed. The void, therefore, is not a simple nothing. It is the ultimate hard drive holding the compressed data for everything that is, was, or ever could be. The universe does not contain information. The universe is information, written on the only surface that truly exists. Yet this infinite energy of the vacuum presents us with a paradox of staggering proportions. The vacuum energy calculated from the sum of all quantum field fluctuations should be immense, a number so large it is effectively infinite. This energy should act as a powerful cosmological constant, causing the universe to expand at a ferocious rate, tearing apart galaxies, stars, and even atoms before they could ever form. The cosmos should be a featureless, accelerating void. Yet, when we measure the actual expansion driven by dark energy, the value is shockingly small. It is not infinite, not even large. It is a whisper, a faint, gentle push that only now, after billions of years, has begun to dominate the cosmos. The discrepancy between the theoretical calculation and the observed reality is the greatest mismatch in the entire history of science. It is known as the cosmological constant problem, and some physicists call it the vacuum catastrophe. The number we predict is at least 120 orders of magnitude larger than the number we measure. To grasp that scale, imagine the difference between the size of a single proton and the size of the entire observable universe. That immense gulf is the difference between our prediction and our observation. Why is the universe not torn apart by its own vacuum pressure? Why is the energy of nothing so quiet? This is not a small puzzle. It is a fundamental crisis, a glaring sign that our understanding of the quantum fabric is profoundly incomplete. One proposed solution involves a concept called supersymmetry. This elegant idea suggests that every known particle has a hidden, super-partner particle. The beauty of this symmetry is that the contributions of these partner particles to the vacuum energy could perfectly cancel out the enormous positive energy from the known particles, leaving behind the tiny, residual value we observe. It is a mathematical balance of cosmic proportions. The problem is, despite decades of searching, we have never found any direct evidence for these superpartners. The Large Hadron Collider has seen no sign of them, suggesting that if supersymmetry exists, it must be in a broken form that does not provide the perfect cancellation we need. Another way to approach the problem is through the anthropic principle. Perhaps the value of the dark energy is not dictated by a fundamental law, but is instead a random, environmental constant. In a vast multiverse, most universes would have a cosmological constant so large that structure never forms, or so negative that they collapse instantly. We, of course, find ourselves in one of the rare universes where the value is just small enough to allow for galaxies, stars, and planets to coalesce, and for life to eventually emerge and ask the question. While this offers an explanation, it feels to many like a retreat from the goal of a predictive, fundamental theory. It exchanges a why for a where. The vacuum catastrophe stands as a humbling reminder. We have peeled back layer after layer of reality, only to find that our most sophisticated theories still struggle to account for the quietude of empty space. The true nature of the quantum vacuum and the reason for its gentle touch remains one of the deepest and most urgent mysteries in physics, pushing us toward a future theory that can finally reconcile the furious mathematics of the void with the serene cosmos we actually inhabit. These ghostly whispers from the quantum vacuum are no longer just mathematical curiosities. A new generation of sophisticated experiments is actively listening, using some of the most advanced technology ever built to probe the properties of empty space itself. In laboratories around the world, scientists are designing instruments sensitive enough to detect the faintest fingerprints of virtual particles and the subtle push of vacuum fluctuations. One frontier of this search involves the hunt for hypothetical particles called actions. These elusive entities were originally proposed to solve a deep puzzle in particle physics, but they are also prime candidates for the mysterious dark matter that binds galaxies together. Crucially, actions are thought to interact incredibly weakly with normal matter, spending most of their time as a component of the quantum vacuum's energy field. To find them, researchers have built powerful, supercooled magnets that create intense magnetic fields. The theory suggests that in the presence of such a field, an action from the vacuum could convert into a faint but detectable microwave photon. It is like trying to hear a single, specific note in a cosmic symphony of static. While a definitive discovery remains elusive, these experiments are already placing stringent limits on the possible properties of actions, chipping away at the unknown and refining our map of the quantum landscape. Another arena for testing the vacuum's nature is in the realm of quantum optics. Here, scientists use incredibly fast and precise lasers to study the behavior of light in ways that reveal the vacuum's influence. They can create states of light where the random fluctuations of the electromagnetic field, driven by the vacuum, are squeezed. This means they reduce the noise or quantum jitter in one property of light at the expense of increasing it in another. By doing this, they can perform measurements with a precision that was once thought to be fundamentally impossible, a direct application of our understanding of vacuum fluctuations. These experiments are not merely confirming old theories, they are opening new doors. They show that the vacuum is not a featureless background, but a medium with properties we can manipulate and explore. As our lasers become more precise and our detectors more sensitive, we are not just observing the quantum fabric, we are learning to pluck its strings. Each new finding, whether a detection or a refined limit, brings us one step closer to answering the most profound question of all. How does the vibrant, energetic nothingness at the heart of reality conspire to build a universe of something? This cosmic perspective forces us to reconsider the most ancient of human questions. Why is there something rather than nothing? For millennia, philosophers have treated nothingness and existence as two separate realms, an absolute void and a world of tangible things. Quantum vacuum shatters this simple division. It reveals a reality where what we call nothing is already a form of something, a vibrant field of potential being. The German philosopher Martin Heidegger grappled with this mystery, questioning the very nature of being itself. He saw nothingness not as mere emptiness, but as an active force that reveals the wonder of existence. Modern physics now provides a startlingly concrete version of this idea. The vacuum is not a sterile absence awaiting creation. It is a foundational state, pregnant with the capacity to generate every star, every planet, and every living creature. The universe did not arrive from some external source into a pre-existing void. It unfolded from within the vacuum's own latent richness. This insight transforms our metaphysical map of reality. The old dichotomies collapse. There is no chasm between nothing and something, only a seamless gradient of potential actualizing itself. Our entire cosmos, in all its splendor and complexity, emerges as a fluctuation that achieved stability, a note sustained from the endless hum of the quantum fabric. This invites a profound shift in how we see our own place in the cosmos. We are not isolated beings on a rock drifting through a dead void. We are expressions of the vacuum's inherent creativity, temporary patterns woven from its endless energy. Our consciousness, our art, our science are all manifestations of the universe becoming aware of itself. This view enriches both spiritual and intellectual journeys, suggesting that emptiness is not a state to be feared, but a source of infinite possibility. The same quantum potential that birthed galaxies also stirs within us, connecting our deepest questions to the fundamental nature of reality itself. Long before equations described the quantum foam, humanity was telling stories about the void. The Babylonian epic Enuma Elish opens with a universe of formless, primordial waters, a chaos from which the gods themselves emerge. The book of Genesis begins with a dark, formless deep, where a divine wind stirs the potential of all creation. In ancient Egyptian myths, a mound of earth rises from the endless, inert waters of none. Greek poets spoke of chaos, the gaping void that existed before all things. These are not mere coincidences of imagination. They are profound, recurring archetypes that resonate with a startling familiarity. Each of these traditions, separated by vast distances and cultures, conceived of the beginning as a state of unstructured potential, a cosmic womb waiting to bring forth form. They used powerful symbols, the cosmic egg containing all possibilities, the dark and featureless waters, the silent and empty expanse. These metaphors for potentiality are humanity's first attempt to grasp the very concept the quantum vacuum represents, a state of latent existence from which everything springs. The parallels are not literal, but they are deeply meaningful. They reveal a universal human intuition, a shared curiosity about how a world of such immense diversity and structure could possibly arise from apparent nothingness. Our ancestors looked into the night sky and told stories of gods shaping the world from chaos. We peer through telescopes and particle colliders, and we tell a story of quantum fields and inflationary expansion. The narrative is different, but the fundamental question is the same. What is the relationship between the unformed and the formed? The quantum fabric, with its seething energy and spontaneous creation, provides a scientific framework for these ancient wonders. It bridges the gap between the mythic and the mechanical, showing that our drive to find meaning in our origins is as much a part of our identity as the atoms that compose us. This recognition does not diminish the scientific story, it enriches it, placing our modern quest within a timeless human context. We are still trying to understand the same cosmic mystery, only now we have new tools and a new language to explore it. These same quantum principles that govern the void are now being harnessed to build machines of unprecedented power. Quantum computers do not process information with simple ones and zeros. Instead, they use quantum bits or qubits, which can exist in a state of superposition, representing both 1 and 0 simultaneously. This ability, along with the strange linkage of entanglement, allows them to explore countless solutions to a problem at the same time. These are not just faster computers, they are engines that operate on the same fundamental rules as the quantum vacuum itself. They are built from the very fabric they seek to understand. One of their most profound potential applications is to simulate the vacuum state of the universe. A classical computer would be utterly overwhelmed trying to calculate the infinite interactions of virtual particles and fluctuating fields. But a quantum computer, speaking the native language of probability and superposition, could model this chaotic dance. It could create a digital twin of emptiness, allowing us to run experiments on the birth of particles from nothing, or observe how the earliest quantum fluctuations might have been stretched into cosmic structures. This offers a new kind of laboratory, one where we can witness the creative processes of the vacuum unfold in a controlled, observable environment. The implications ripple across physics. Such a machine could tackle problems that have remained unsolved for decades, like the precise nature of quantum gravity or the true resolution of the vacuum catastrophe. It could allow us to simulate the conditions of the first moments after the Big Bang with a fidelity we never thought possible. As these technologies mature, we are not just building tools for calculation. We are constructing a new kind of lens, one that might finally allow us to see the loom on which reality is woven. The quantum fabric which gave rise to everything may ultimately provide the key to understanding its own deepest secrets. This endless branching of possibility leads us to a breathtaking conclusion about the nature of reality itself. The many worlds interpretation of quantum mechanics suggests that every single time a quantum event has multiple possible outcomes, the universe does not choose one. Instead, it splits, realizing every single possibility in its own separate, newly formed branch of reality. When an electron is measured, one universe sees it spin up, while another, equally real universe sees it spin down. When you make a choice, versions of you live out every alternative in parallel worlds. This is not science fiction, but a serious, albeit controversial, consequence of the quantum equations. The multiverse, then, is the ultimate expression of the quantum fabric's creative potential, a cosmic tree with infinite branches, each sprouting from a random fluctuation or a quantum decision. This idea finds a powerful ally in the theory of cosmic inflation. The same mechanism that blew up our universe from a quantum speck could be an eternal process, happening over and over again in a much larger meta-universe. In this eternal inflation, different pockets of space stop inflating at different times, each one becoming a separate bubble universe with its own unique local laws. Some of these bubbles might have physics wildly different from our own, with forces and constants that would make matter or life impossible. Others might be almost identical to ours, with only the slightest variations. In this grand panorama, our entire cosmic history is just one bubble among an infinite froth of universes, each a unique crystallization of the vacuum's latent energy. What does this mean for our sense of uniqueness? If every possibility is realized somewhere, then our existence is not a singular, miraculous event. We are not the winners of a 1 in a billion cosmic lottery. We are simply the inhabitants of a universe where the quantum dice landed in a configuration that allows us to be here to ponder the question. The fine-tuning of the constants of nature is not evidence of design, but of a cosmic sorting process. In an infinite multiverse, every possible combination of physical laws will exist somewhere. We, by necessity, find ourselves in one of the rare, hospitable branches. This radically redefines probability. A seemingly unlikely event is not improbable across the entire multiverse. It is a certainty. Somewhere, a version of you is living a life shaped by every choice you did not make. The quantum fabric does not favor one outcome, it generously manifests them all. The void is not a single origin story, but an infinite library of every story that can ever be told. So where does the relentless flow of time come from? This directionality, this arrow pointing from a definite past toward an open future, may be the most profound structure to emerge from the quantum void. In the deepest laws of physics, most processes are time-symmetric. They work just as well running forward or backward. yet our experience is a one-way street. We remember yesterday but not tomorrow. This asymmetry, the arrow of time, finds its roots in the concept of entropy, a measure of disorder that always increases. The universe began in a state of incredibly low entropy, an exceptionally ordered and uniform configuration originating from the pristine vacuum. As the cosmos evolved from that initial state, the quantum fluctuations were stretched, creating pockets of higher and lower density. Gravity then began its slow work, pulling matter together into galaxies and stars, a process that further increased the universe's overall disorder. The journey from a smooth, high-energy vacuum to a lumpy, structured cosmos is a one-way trip driven by this growth of entropy. The flow of time, then, is not a fundamental feature of the quantum fabric, but a large-scale consequence of its unfolding. It is the story of potential becoming actual, of symmetry breaking into diversity. Think of a drop of ink carefully placed in a glass of water. Initially, it is a highly ordered, low-entropy state. The moment it is released, it begins to spread, mixing chaotically into the water, increasing the disorder until it is fully blended. This process only goes one way. You would never expect the scattered ink particles to spontaneously gather back into a single, neat drop. Our universe is like that. It started as an orderly drop of pure potential in the quantum vacuum and has been mixing and evolving into the complex cosmos we see today. The arrow of time is the direction of that mixing, the path from simplicity to complexity. This connects the personal experience of time's passage directly to the cosmic conditions set at the beginning. The reason you can remember the past but not the future is because the past is a state of lower entropy, a moment when the universe was more ordered. Your consciousness, your very ability to perceive change, is tied to this grand cosmological process. The timeless emptiness of the quantum vacuum, therefore, did not just spawn matter and energy, it gave rise to the river of time itself, a current flowing from the singular order of the beginning toward the vast, structured complexity of the present. This leads us to one of the most speculative and fascinating frontiers of all, the possible connection between the quantum fabric and the mind itself. A small but persistent line of scientific inquiry asks whether consciousness could be more than just the product of neurons firing. Could it be an emergent property of quantum processes occurring within the brain? The most well-known version of this idea is the orchestrated objective reduction theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that the seat of consciousness lies within tiny structures inside our neurons called microtubules. These protein scaffolds they propose are not just structural. They could be capable of processing information and maintaining quantum states like superposition and entanglement in the wet, warm environment of the brain. In their view, a conscious moment occurs when such a quantum state reaches a threshold and collapses, or reduces, in a way that is orchestrated by the brain's biological structures. This collapse is not random but influenced by fundamental geometry in space-time, linking the process directly to the foundational level of reality, the quantum vacuum. This is a breathtaking claim. It posits that our subjective experience, the feeling of being, is not a classical computer-like output. Instead, it is a quantum phenomenon, intimately tied to the same seething vacuum fluctuations that gave rise to the cosmos. Your thoughts, in this view, would be a manifestation of the emptiness becoming self-aware. Yet this theory is met with significant and valid criticism. Primary challenge is the issue of decoherence. Quantum states are incredibly fragile. They are easily disrupted and destroyed by their environment, a process that happens almost instantly in a warm, noisy place like the human body. Critics argue that the brain is simply too hot and too chaotic for delicate quantum coherence to persist long enough to influence neural processes. For most neuroscientists, classical physics and chemistry are more than sufficient to explain the brain's workings. Furthermore, this hypothesis bumps directly into the hard problem of consciousness. This is the profound mystery of why and how physical processes in the brain give rise to subjective, qualitative experience. Why do we have feelings, sensations, and an inner life? Simply shifting the problem from a classical to a quantum framework does not, in itself, solve this hard problem. It merely moves the mystery to a different layer of reality. So where does this leave us? While the evidence for quantum consciousness remains highly controversial and outside the scientific mainstream, the idea serves a powerful purpose. It challenges us to think more deeply about the nature of awareness and its place in the universe. It forces a conversation between the physics of the very small and the phenomenon of inner experience. If there is a connection, however tentative, it would complete a profound circle. The same quantum potential that ignited the cosmos and spun galaxies from the void would also be the source of the mind that contemplates it. We would not just be living in the universe, we would be the universe experiencing itself, a thought born from the vibrant nothingness. This new vision of reality, where we are born from the restless hum of the void, cannot help but reshape our deepest sense of self. If every thought and action is, at its core, a complex arrangement of quantum events, where does that leave our cherished notion of free will? We feel like autonomous authors of our own lives, yet the underlying physics presents a universe that is both deterministic in its laws and probabilistic in its outcomes. This is not a contradiction, but a call for a more nuanced understanding. Our will might not be a mystical force breaking the chains of cause and effect. Instead, it could be the profound and complex expression of those very chains operating at their highest level of organization. You are not a ghost in the machine, you are the machine itself, a dynamic pattern woven from the quantum fabric, capable of reflection, choice, and change. This perspective does not diminish our responsibility. It grounds it in the very substance of the cosmos. Every decision you make is a real ripple in the field of possibility, a tiny act of cosmic creation. This realization can be a source of both humility and immense empowerment. It invites a profound sense of interconnectedness. The same quantum fields that animate your consciousness also ripple through every other living being, through the air you breathe and through the distant stars. The illusion of separateness begins to dissolve, replaced by the recognition of a shared origin in the vibrant emptiness. This interconnectedness can become a foundation for a new ethical awareness. If we are all temporary expressions of the same underlying reality, then compassion and cooperation are not just social virtues, they are acknowledgments of a fundamental unity. Understanding our quantum origins can transform existential anxiety into a deep and abiding awe. The universe is not a cold, indifferent mechanism. It is a continuous creative process, and we are not merely passengers but active participants in its unfolding story. Our daily lives, with all their struggles and joys, are part of this grand narrative. To embrace this knowledge is to find a new kind of meaning, one that celebrates our fleeting, beautiful role in the endless dance of the quantum void. The same emptiness that birthed the cosmos might one day become our greatest tool. Emerging research is exploring how we could potentially manipulate the quantum vacuum itself, not just observe its effects. The concept of extracting usable energy directly from this seething void has long been a dream, though it remains firmly in the realm of theoretical physics. The central challenge lies in the vacuum's uniform nature. Its immense zero-point energy is everywhere at once, a constant background hum. To harness it, you would need to create an imbalance, a gradient from which work could be extracted, much like the Casimir effect does on a microscopic scale. But scaling that phenomenon up to a practical level presents monumental engineering and fundamental physics hurdles that we have not yet overcome. Yet, the potential is so profound that the speculative work continues, pushing the very boundaries of what we believe is possible. One of the most tantalizing ideas involves propulsion. The Alcubierre drive, a concept grounded in Einstein's equations, proposes a way to effectively travel faster than light without breaking relativity. It would not propel a ship through space, but instead manipulate the fabric of space-time itself. Imagine creating a bubble where space contracts in front of the vessel and expands behind it. The ship would surf this wave, riding inside a pocket of normal space-time while the quantum fabric around it moves at superluminal speeds. This warp drive would require the engineering of space-time's geometry, potentially by using exotic forms of energy with negative pressure, a property that dark energy suggests might indeed be inherent to the vacuum. While the energy requirements are currently astronomical and the existence of such exotic matter is unproven, the idea illustrates a future where we don't fight the universe's rules, but work with its deepest substrate. We are already taking the first tentative steps toward such control. In advanced laboratories, scientists are learning to engineer vacuum states. Using superconducting circuits and other quantum technologies, they can create confined spaces where the properties of the quantum field are altered, effectively designing a custom vacuum. This is not about creating energy from nothing, but about sculpting the vacuum's potential to perform specific tasks, like enabling more sensitive measurements or protecting fragile quantum information from decoherence. These are the baby steps, the first time humanity has begun to pluck the strings of the quantum fabric with intention. The ultimate challenge is to move from observation to interaction, from understanding the vacuum's music to learning how to compose with it. What if we could dampen quantum fluctuations in a specific area to create a perfectly stable platform for a next-generation telescope, or conversely, amplify them to stimulate the creation of particle pairs? The ability to manipulate the void would transform our relationship with the universe, turning the fundamental background of reality into an active medium for exploration and innovation. This journey to command the quantum vacuum is perhaps the next great human endeavor, a quest to gently guide the hand that wrote the cosmos into being. But how do we translate this cosmic poetry into a language anyone can understand? The challenge of sharing the quantum vacuum story is not just for physicists, it is for every educator, parent, and curious mind. We start by replacing intimidating jargon with the magic of a well-told story. Instead of explaining quantum field theory, we can invite someone to picture the entire universe as a vast, invisible ocean. We cannot see the water, but we can see the ripples on its surface, and those ripples are everything we call reality. This simple shift in framing transforms an abstract concept into a tangible, almost familiar image. An effective analogy acts as a conceptual bridge, allowing a person to cross from what they know to the wonder of what they do not yet grasp. Think of the quantum vacuum as a cosmic seed. To a casual observer, a seed appears small, brown, and inert, a speck of nothing. But hidden within its tiny shell is the entire blueprint for a mighty tree, with its sprawling branches and complex ecosystem. The seed is not empty, it is a pocket of immense potential. In the same way, a single point in the quantum vacuum holds the latent potential for galaxies, stars, and life itself. This kind of comparison makes the incredible feel intuitive. Interactive models bring this hidden world to life. Imagine a classroom where students use a stretched fabric to represent space-time, placing marbles to see how mass creates gravity wells. Now imagine a version of that model that also vibrates with a gentle, constant hum, demonstrating the zero-point energy that exists even when the fabric is flat. Or picture a digital simulation where particles and their antiparticles flicker on a screen, appearing and vanishing in a dynamic dance, allowing young learners to visualize the Casimir effect as a push from an unseen crowd. These tools are not simplifications, they are invitations. They allow hands and minds to engage with concepts that are otherwise locked away in complex equations. The goal is to spark a sense of personal discovery, to create that moment of awe when a student realizes they are not just learning about the universe, but are a part of its fundamental fabric. By demystifying the quantum void, we do more than just convey facts. We empower a new generation of thinkers, innovators, and explorers. We give them the conceptual tools to see the world not as a collection of separate objects, but as a unified, dynamic, and deeply mysterious whole. This is how we ensure that the journey of cosmic discovery does not end with us, but continues to unfold in the minds of those who will one day ask the next great questions. This cosmic perspective does not have to remain an abstract theory. You can begin to feel its truth in the quiet moments of your own life. Think of the simple act of sitting in a garden. The warmth of the sun on your skin is a cascade of photons, ripples in the electromagnetic field that began their journey from a quantum frenzy at the sun's core. The solidity of the ground beneath you is an illusion of scale, a temporary stability in a whirlwind of quarks and electrons dancing to the hum of the Higgs field. When you breathe, you are drawing in atoms that were forged in the heart of ancient stars, each one a testament to the universe's journey from a smooth vacuum to a structured reality. This is not just a poetic thought, it is a physical fact. By consciously recognizing this, a walk in the park can transform into a journey through cosmic history. You are not just a visitor in nature, you are a manifestation of its most fundamental processes. This shift in perception is a form of mindfulness, a way to anchor your awareness in the vibrant, interconnected reality that physics reveals. It is about seeing the extraordinary woven into the fabric of the ordinary. A practical way to cultivate this is to pause for a moment each day and focus on a single, simple object, a leaf, a cup of water, your own hand. Instead of seeing its name or its function, try to perceive it as a temporary knot of energy, a localized vibration in the quantum fields that fill the cosmos. Notice its texture, its temperature, its light. This object, like you, was not here at the dawn of time. It coalesced from the potential of the void, and one day it will return to that state. This reflection does not diminish its reality, it enriches it with a profound sense of context and belonging. You are not separate from the universe you observe. Your very act of observation is a part of the cosmic process, a ripple in the field of consciousness that itself may be deeply connected to the quantum fabric. Embracing this quantum awareness encourages a holistic outlook where personal challenges and joys are seen within a grander, more resilient framework. Your life becomes a unique expression of the universe exploring itself, a brief but brilliant flash of patterned starlight in the endless creative